So thank you all for coming. I'm Michelle Gill, and I'm a senior data scientist at Metis. My background with data science is, I guess, very broad. I'm trained as a biophysicist, and so I did research for the government and in academia. I also have worked as a management consultant, so I've sort of spanned the whole realm of data science, if you will, from one extreme to the next. And I'm currently at Metis. And Metis, just a little bit of a background, we offer data science training. So that it comes in several forms. The first is with a 12-week data science bootcamp that's in person, and it assists individuals who are making career transitions from a broad range of fields into data science. And those boot camps are held in New York, San Francisco, Chicago, and Seattle. We also do corporate training in a broad range of topics, Python for data science, machine learning, natural language processing, Spark, all of those sorts of good things. Finally, we have evening professional development courses, and then we have an online training offering which is called Explore Data Science. So really quickly, it's fun to get a temperature of the room. Who's programmed in Python before? So mostly everyone. Okay, who's used machine learning before? Okay, and natural language processing? A little bit? Okay. So today we'll start basic and get a little broader. These sessions are always way more fun if it's interactive, so I encourage you to stop me, interrupt me with questions. If you're stuck on something, again, interrupt me. We can try to clear it up then or add breaks. I'm always happy to help. Okay, so the reason we're all here, there are oodles and oodles of data that's generated every minute on the internet. Lots of it is in the form of text, via email, text messages, news articles, blogs, Twitter, reviews. Just a huge volume of data generated by mankind is in the textual form. And so being able to use that data to do things like search and classify articles is incredibly important. So I alluded to the first 2 points, but information retrieval from text, classification and clustering of these articles. So Google News, when you drill down on topics, is a very nice example of classification and clustering of articles. Sentiment analysis, what is the writer of this article feeling? What is their intent? That can be incredibly useful information to be able to automatically glean from a piece of textual work. Lastly, recommendation systems. When you search for things on Amazon, on Google, the little Amazon ad, the little strip of products that you might be interested in, all of that has some basis in NLP and machine learning. So the challenge becomes then, how do we represent text? So for those of you who've done machine learning before, typically features are encoded in some sort of numerical format, be that binary, ordinal, so 0, 1, 2, 3, by floats, etc. So that's a challenge with text because most of it doesn't lend itself readily to that type of encoding. So that is sort of the fundamental challenge that we have to overcome when we're dealing with capturing data and in the form from text and using it for machine learning. So there's a couple ways that we can do that. So the first involves splitting the text into words. So this is called tokenization. So if we take the sentence, this is an example, we can split it into 4 words. Once we've tokenized our text, we can encode it. So if you have a background in machine learning, sometimes one-hot encoding is the term that's used to describe this. We can create a vector where there are, we can create a vector where there's a 1 representing each of the words and then a 0 everywhere else. And that's going to be a lot of the basis for the techniques that we're going to learn about and put into use today. So once we've encoded these words, we can then represent the documents by their tokens. So this is called a document term matrix. If you transpose it, sometimes it's called a term document matrix. So if we have 3 different documents, each occupying a row of this matrix, the words that are found in each of these 3 documents can be populated vertically with a 1. So it's sort of a grid that helps us understand what words appear in which documents. And this will be the foundational means by which we encode our text data. So to give you just a flavor of how we're going to do this, we'll go into the Python text in a lot more detail in the workbooks that you downloaded from GitHub. But scikit-learn has a number of features to encode text. So one that we'll be using today is called count vectorizer. And if we take a corpus, and the corpus is simply a collection of documents. So this is a short corpus with 3 documents, each with 1 sentence each. And we'll encode those and tokenize this text, and then use count vectorizer to transform this into a matrix that we can see here with Python. And so each of the words is vertically on top, and then each of the documents is represented as a row, and there's ones encoding the existence of a word. Any questions before? Does that make sense? Okay. So who thinks that's all we can do with text data? No. I see 1 no, 2 no's. Yeah, there's a lot more we can do. So we're going to go into that. How much information is contained in a word? Is it just the word? Is it just the characters? It's a lot more than that. We can encode things such as multiple words together. That helps us understand and capture word order. So, for example, New York, where I'm from. New and York are 2 separate things when taken apart. When put together, they mean something really different. So it's important sometimes to encode these types of features. That's called n-grams, which we'll get into later on. Sometimes and often we want to remove capital letters so that the word ran, when it's capitalized, looks the same as ran when it's not capitalized. We often want to remove common words, a, an, the. Those aren't really helpful with understanding the meaning and the intent of our documents. Co-occurrence of words, as I mentioned. Sometimes we want to convert words into their root form. So if we take the word running, a lot of times we want that to show up as being identical to ran or run. So there's ways to do that, and we'll cover those. Misspellings are always a challenge to deal with. Those are hard to encode unless you know specific examples, but they come up. Different languages, different characters in languages, those are all big challenges with natural language processing. Finally, do we weight each word equally, or do we not? Are there some words that are really important in understanding what the intent of the document is and how it associates with other documents? So all of this is collectively called pre-processing, and you can pre-process text data for hours. And the short answer is with some of these, you just have to try things. Some of it is situationally dependent, whether particular types of pre-processing will work or not. But the short answer is, like with all machine learning, a lot of it is iterative and empirical. You simply have to try it, try different methods, and see how they work in your model. OK, so let's look at a couple examples of pre-processing before we dive in and do some of the processing together. So common words such as the and I and a can be removed. These are usually called stop words in natural language processing. And we can get lists of stop words from NLTK, which is a text processing library. We can also get them directly from count vectorizer from sklearn, which I mentioned, and it will take them out. So if we have a sentence that says, this is an example with stop words, and we want to remove them when we create our document term matrix, what we get is below, example, stop, and words. Everything else in that sentence has been removed. So that's an example of how stop words can be removed from a text document during processing. So words can be reduced to their root. This is often called stemming, and there's another related technique called lemmatization. So this takes the words run and running and makes them identical. Lemmatization generally is a little bit more aggressive than stemming. It also takes a little bit longer. I personally find that I tend to get better results with lemmatization. So we'll cover both of those today. And I have some automated functions that handle lemmatization that we'll use. OK, so word order can be captured by joining words together. Again, back to the example of New York very different when it's separated as one word. So these are called n-grams. So the simplest form, which is just one word, is usually a unigram. When you put two words together, that's a bigram. You can do trigrams. The challenge with putting lots and lots of words together, if you keep track of all of those, it becomes really, really large. So realistically speaking, bigrams, maybe trigrams, if you have a very large set of data, would be about the biggest you're going to end up using. So other sort of pre-processing considerations, and some of these are really difficult to understand how to capture with text. So what about implicit assumptions? So we have the sentence, Jane no longer writes fiction. That means that Jane wrote fiction. What if we're trying to classify articles about authors? So these things are challenging, and sometimes there's a lot of intricate feature engineering that can go into designing how to convert text into numerical features. What about word relationships? So red and blue often go together. Maybe Saturday and Sunday go together as the weekend. Co-occurrences, car and drive. A lot of these are captured well with deep learning, which we'll cover a little bit at the end, hoping we have time. A big challenge, as I alluded to with n-grams, when you start getting very, very large, very complex features, there will be a lot of sparsity in your data, and it becomes very high dimensional. So there will be lots and lots of columns in that term document, or the document term matrix that we talked about. That gets to be a challenge computationally speaking, and it gets to be a challenge with modeling many times. So one more sort of esoteric consideration before we go on to walk through some pre-processing examples and a few exercises. So how do you embed the meaning of a sentence into numerical form? It's quite a challenging one to think about. We talked about there's ways to tag parts of speech. So you can tag things like a verb or a noun. But how, and that's useful, but it doesn't quite get you to the point of how to encode the bigger parts of a sentence. A prepositional phrase, things like that can become really challenging. And I would not say that right now we have great solutions to those, other than things which are maybe sort of custom built by the modeler, him or herself. So any questions before we move on? And we'll do some walkthroughs and exercises. Everyone good? OK. So if we go to, if you open the first, if you fire up Jupyter, and I'm going to mirror my displays, and open, so there's a file called accessory functions. So for those of you who have downloaded or attempted to download NLTK, you'll need to edit this file right here and give it a path to your NLTK data. It'll probably be your home directory if you downloaded it as described. And then for those who are able to download the Google vector files, you'll need to set this path as well. This only needs to be done once. For those of you who weren't able to download the Google vectors or the NLTK, I'll try to catch up with you during the exercises. The Google vector file is only required at the very, very end. So if you're having trouble with that one, I would say don't worry about it for the time being.
Keep that zipped?
Yes, leave it zipped. So this is, my apologies, this is just, there's a Python file called accessory functions in the notebooks directory.
I'm sorry, what was that for launching?
For launching Jupyter. If you installed it on your Windows computer, it's probably a program. Try Jupyter Notebook.
Okay. I'll probably type that and I just.
Yeah, try Jupyter Notebook. Yeah, if you just navigate to the notebooks directory, that's where this file is. OK, is everyone good with that? All right, so let's then walk through the processing of some text to get together. So this is notebook 1 called Text Preprocessing Walkthrough. And so we'll do some examples of natural language processing. So you'll need to have the NLTK library installed. And we can just walk through these together. Go ahead and execute the first cell. Is everyone good with executing things on Jupyter?
I don't know where to find what I downloaded. I have Jupyter notebooks. So I did that, and then it opens up this, but where do I find all that stuff?
So I would navigate to the directory. So where are you at? Can I just do?
Yeah.
So can you go to inside the ODSC directory?
Where's that?
The Git, the presentation material that was downloaded from GitHub.
Oh, I see. I know. What's over here? And here.
So if you go to, can I see?
Yeah.
So Python learn. Can you drag it? Oh, thank you. I've never done it that way. Thanks. Yep. All right, so is everyone good before we start? Yes? Okay. So, got it? Okay. So you'll need to set your path to where you downloaded NLTK. There's the file called accessoryfunctions.py. Yeah, it should be your home. Okay. So if we execute these files, so we'll create a simple corpus with 3 documents, very, very short. This is document 1, I went running. Document 2, she was a writer. And then a document with some numerical values in it, in the sentence. So normalization is generally referred to a number of tasks. One of those is making all of the text lowercase. And the other one I tend to lump in with normalization is removing numerical values. So this sentence that ends in $4,000, we'll want to remove that usually. So again, this is just to give you a flavor of how this works. So we're going to, I wrote a little function that we can use to take and make our string lowercase. And then the second part of that function, we'll take and use what's called a regular expression to remove the numerical values from the text. And so if we execute that, we can see this is document 1. I went running. Is everyone good on that? Okay, cool. Similarly, we want to remove punctuation from our sentence. So there's a nice little string of punctuation built in to Python in the string library. And we'll use a regular expression again, just like we did to remove the numerical values. We'll remove the string from the library. And here we just compile it and encode it. So that's what this line does. So we've removed then all of the punctuation, the periods, the commas, the semicolons from our document. So tokenization. This is splitting our document up. And commonly, tokenization is done in the form of words. So you would split every sentence into its word components. Alternatively, sometimes it's useful to split something up as a sentence. So it's possible to do both. So this is just an example of sentence tokenization. I didn't store this for various reasons, but you can split our 3 documents up by their sentence. Alternatively, and more commonly, we'll split them by words. So this splits every single word up And effectively, we lose the sentence structure of our document. And this is done with word tokenize, which is just a function that's in NLTK. You could also, if you like regular expressions, like splitting strings, you can do it that way too. All of those are totally valid ways to do this. Yep. Do you have NLTK installed? Well, I'll come talk to you when we start on the exercises. Okay, so stop words. Again, these are words like I, a, we, are. You can see the list of some of the stop words that NLTK contains that it'll remove automatically from your corpus for you. And this is a simple function to make everyone's lives easier. It will handle our documents in single or as a list of lists where we had our 3 documents combined together. So nothing specific to NLTK. But if we execute both of those cells, we can remove the stop words. So we have document 1 went running, and everything else then is gone. Document 2, writer, document, numerical entry. So all of our stop words have been removed. So a couple more, and then we'll start on some exercises, and I can help those of you who are having installation and Python challenges. So parts of speech tagging, again, things like nouns, pronouns, adjectives, verbs. NLTK has something called, NLTK has something called position tag, which will handle that. And so you can see it returns, this is called a tuple in Python, and it has the first part of that is the word itself, and the second part of that is the part of speech. So we can use that to build features later on. The next part of the next step that we're going to use also will use these tags to help infer meaning from the words. Mm-hmm.
When you do the parts of speech analysis,
Mm-hmm.
how accurate do you find it?
I would say not extremely accurate. There are more sophisticated parts of speech taggers that do better. They are computationally more expensive. To be sort of honest, I don't use parts of speech tagging directly as a feature. When you do lemmatization, which I said I prefer lemmatization, it likes parts of speech tagged. So if you give lemmatization parts of speech the tag, it will do a lot better job in truncating the word, fixing the word tense, etc. So I actually use it for that. One challenge with NLTK is the tag format that lemmatization wants is not the tag format that's in NLTK. So I have a function that converts things that I just use and that I have included today. But it's a challenge with NLTK. I wish that was.
Mm-hmm. Do you use, does it also work, does the part of speech tagging work with diagrams? So machine learning?
You can engineer features that way, absolutely. So usually what you'll do is tag it like this, and then you can separate them out and create your bigrams with your words and create your bigrams with your parts of speech. And then you can sort of join the matrices together, like join your count vectorizer matrices. So if you wanted to do that, yeah. It'll make your feature space really big. So you may only want to do it for important instances, yeah. But yeah, good question. So stemming is, will reduce words to their simplest form. So running to run. I kind of alluded to this in the previous question that I just answered, but it's a little bit simpler than lemmatization. For right now, we're just going to do stemming. We'll talk about lemmatization later in the exercises. So this will take snowball stemmer, which I always thought was kind of a cool name. There's a variety of stemmers in NLTK. Snowball stemmer is the one I tend to use. And this will take and apply stemming. So you can see we went from run to running, or from running to run, excuse me. And it also did not such a great job on numerical. It changed it to numer. So that's sort of one of the challenges that I often encounter with stebbing, which isn't to say that you should never use it, but I often find the results a little bit frustrating. And entry with a Y became entry with an I.
Isn't that so that entries and entry go to the same?
Right. Lemmatization will do better on those things, though. It'll change it all to entry. It'll figure it all out.
So is there ever a reason to take these stemmed versions and then like transform them back into their originals? Is that something that's even possible?
I have never done that. If you wanted to do that, you'd have to, like, you could make a dictionary of all the things that are different before and after, and then invert. I mean, that's a really simplistic way to do it. But I've never done it. It's often, though, I look at words that have been stemmed and think, what word was that? So yeah, it's absolutely, you could do it that way. It would be a little bit manual, and depending upon how long your corpus is, maybe a little bit slow. So we can create n-grams. There's a couple of ways to make n-grams. This is with the NLTK library. We can also make n-grams with count vectorizer itself when we encode our document as a numerical form. So I made a little function that will create bigrams using the NLTK n-gram list. And so notice that this goes along each word that's in a document and then joins it. So document 1, and then 1 went, and then went running. So it captures every position, that word, and then the next word beyond it. And so if you have multiple sentences, it's obviously going to take the end of one sentence and join it to whatever remains of the next sentence. It's just something to consider. It's kind of the way n-grams work. If you wanted to get more sophisticated and not do that, you could do sentence tokenization and then maybe do the n-grams just within your sentence and then sort of put it all together. It'd be a little bit messy, but you could definitely do that. I would say the one thing you'll find, it's easy to worry about lots of these little things when you're sort of thinking about how to pre-process your text. In a lot of cases, I would say the smaller things sort of just come out in the wash in the end. With machine learning, there's always a lot of noise in the data, and this is that's effectively a little bit of noise. So this is the final part of the walkthrough. So count vectorizer, as I said, is one of the ways that we can create a document term matrix with our data, turn our text into numbers that we can feed into a machine learning library or a machine learning model. So this is really well set up within sklearn. It's sklearn.featureextraction.txt. You import count vectorizer, and you can fit it, or you can fit and transform it. Darn it, sorry, it keeps jumping on me. You can fit and transform it, and that will return a sparse matrix. So, darn it. That will return a sparse matrix. So if I alluded to this earlier, there can be lots of features in textual data, so it will encode it in a way that doesn't require all the zeros to be saved. If you want an array out of it, you can run this function or this method .toArray, and that will convert it into a standard NumPy array for you. Okay, so that's our document term matrix. I find them a little bit easier to view, at least for teaching purposes, to put them into a pandas data frame. So there it is encoded, and you can see all of the individual words on the top. One thing to notice here on this data frame, $000 is on the left. So count vectorizer does not remove numerical words, so alphanumerical words. So I often will take and remove them beforehand. There's a little regular expression I wrote that will do that. If you're going to do that with count vectorizer, you also need to make your words lowercase, because that's part of what count vectorizer does. And then you can feed this function to Count Vectorizer as a preprocessor. So this will get rid of the numbers, the alphanumerical words for you. Last couple points. So we've been numerically encoding our words with Count Vectorizer. That will give you a count for each word every time it occurs within a document. Sometimes that's more than what we want. Sometimes maybe we just want like a binary representation of a word. So I don't want the word cat to appear 10, to have a value of 10 if it's in my document. I just want it to have a value of 1. So you can feed Count Vectorizer, there's a flag called binary, and that it will take care of that for you. And so you can look at the min-max of those, and they will, if you have a bigger document size, that'll give you ranges that are only 0 and 1 for binary encoding. Lastly, n-grams, and I think this nicely makes the point about expanding feature space. So if we give that an n-gram of range 1 and 2, it will do unigrams and bigrams. So it will go through the document and pick out every word individually, and then it will also get every bigram as a feature. And this is actually, I transposed it so that you can see it. It's obviously decently sized even for something so simple. So I think it nicely makes the point that this really causes your feature space to expand. Last point before we do some exercises. So Count Vectorizer can take out the stop words for you. You can feed it a list of stop words. You can feed it our stop words list that we imported from NLTK earlier and do the same sort of fit transform and get out your numerical matrix. So can I answer any questions about that before we do some exercises?
You mentioned a flag-specific way to sort the words.
So we'll cover that in shortly. As a general rule, if you want words that appear less frequently to be viewed as important, there's an alternative to Count Vectorizer called TF-IDF. It stands for Term Frequency Inverse Document Frequency. We'll cover what that means, but it will effectively have words that appear less frequently. Their weight is not diminished as much as just numerical counting. It also can take into account words that appear in fewer documents. So there's ways to do that. Any other questions? So there's some exercises. Let me scroll to the top. If you go to Notebook 2, there are some exercises, and I'll give you 15 or 20 minutes. We can work on them and talk about them, and I'll circulate around the room. If anyone has problems with installations, I'll try to catch you at the beginning of this. Okay? So we'll be using a small document set. It's SMS, so text data, and they're classified as either spam or ham. So I'll get you started. I have a lot of the imports set up. I find things easier to handle with pandas. If you're not a pandas fan, you can convert what I imported to text with this function here. And that'll give you a list and then of your labels and also of your documents themselves, if you don't like pandas. And then there are a series of questions to work on, and I'll circulate. Okay, how's everybody doing? I would say that text preprocessing is tedious and sometimes frustrating. So if you start to do a lot of NLTK, I have sort of a standard library of functions that I just keep to sort of do some of these things for me. So I'll show you one of those very briefly before going over the answers. And then to save you pain on the future exercises, I sort of did the cleaning for you. So because I've been there. So if you go to accessory functions, I'll show you the function very briefly. So this was the same Python file where you set the paths for NLTK and the Google vectors. And so there's a couple things. So I mentioned, we discussed a little bit about challenges with lemmatization. So there's a function that will handle the conversion of parts of speech tagging for lemmatization. The second function that we'll be using, and this is the primary function, it will handle a whole bunch of steps for pre-processing text data. So it will take you through making the text lowercase and removing alphanumerical words. It will remove punctuation, tokenize them. It removes stop words. It'll do parts of speech tagging for you, and then it does the lemmatization, and then just spits it all back out for you. So it will save you pain in the future exercises. So let's go through these a little bit quickly. So I tend to use pandas. Again, as I said, you don't have to. But after we import the data, so the number of text messages you can get simply by doing the length of the data frame or the list if you converted it to a list. Pandas has nice ways to measure, to quantitate the percent composition. So with the label, you can do value counts. And we can see that we have 86% ham. The remaining percentage is spam. And so then message length, you can do a map on the length. And I just shortened the list. So there's messages that are of length 22. There's 120 of them. So it's just a very simple way to measure message length. Exploring your data, which is essentially what we're doing here, is often a useful way to determine what types of feature engineering you need to do with NLTK, with cleaning your data and pre-processing. So it can be useful. So I should have been a bit more explicit. This is the answers notebook for exercise 2. And so all the answers are in there. So here, again, this takes you through some of the cleaning and the normalization, which again, you're not going to have to do after this. So here we removed any alphanumerical words. This is the same. This is called a regular expression. A couple of you asked about this. There's a joke about regular expressions that I like. I had a problem. I tried to solve it with a regular expression, and now I have 2 problems. I always tell the boot camp students that. Because regular expressions can be challenging. So this will do something similar. It's a similar regular expression. It'll remove the punctuation. So now we see the exclamation points gone, commas are gone, periods are gone, etc. And I would normally not recommend, so because this is educational, I kept tacking on columns successively of the cleaned data. Normally you would not want to save all of that because it starts to take up memory in your computer, but I was trying to demonstrate sort of the transition. So here's where the data are tokenized. You can see the tokens column is everything is a list. And then we can figure out the most common words. Some will take a list. This empty list will take a list and accumulate everything so that you can sort things. And so now we can convert it to a dictionary. Counter will effectively make a histogram, so we can find the most common words. So finally, stop word removal. So this is the token stop. You can see is removed from hi Mandy, is Sullivan. So that's removed, or hi is Mandy Sullivan. So I mentioned this when I showed the convenience functions earlier. This will convert the nomenclature that NLTK uses for parts of speech tagging, verbs, adverbs, etc., to a nomenclature that the lemmatization function likes, which we cover later. So here on the right, you can see tokens, parts of speech. So again, they have R, N to indicate what part of speech. So here's stemming. So again, stemming gets rid of the ends of words. One challenge that I always find, so early with a Y was changed to early with an I. Purchases, instead of making it purchase, it's purchase, I guess. So we're missing an E. So I'm going to transpose this one. Ooh, I must not have executed that cell.
Are there other stemmers?
There are. There's lots of them. I tend to use Snowball. A long time ago, I decided I had better luck with it. I wouldn't necessarily say that's a conclusive scientific study. You'll find that as you do, if you do a lot of this, you sort of get habits. So I tend to use Snowball. So I, again, tend to find better luck with lemmatization. So this is transposed. So early, you can see a very strong example of that here. So token stem early is an I, and then lemmatization got it right. It left it alone. So that's why I tend to feel like it's worth the effort of doing the parts of speech tagging to do lemmatization. And again, if you get some functions written, you can make your life easier. I was just comparing sort of the results here for your benefit. Here are all the words that were different with stemming and lemmatization. And so the one on the left is the stemmed word, and the one on the right is the lemmatized word. So you can see all the things that sort of tend to work better, in my opinion, with lemmatization. Okay, and then I saved this file. You all have a copy of this if later on you want to play with it. I just saved it as a pickle. Yep, what's up?
From an analytical perspective, does it really matter whether it's what it's choosing as the stem, as long as it's a unique and term, right?
More importantly, I would say as long as it's consistent. Right. Yeah, so you can definitely make that argument. I think interpretability becomes a bit more challenging when it's doing goofy things with the words. But you're right. Stemming can work just as fine as long as it consistently turns earliest, early, earlier, all of those to early with an I. It's not such a big deal. If you want to go back and find what that word actually was, early is not so hard, but sometimes that can be more challenging. So sort of pros and cons. Lemmatization is slower than stemming, for sure.
When you're working in a specific context, do you ever find the need to modify the stop list?
Yes. So wine is something that I quite enjoy, and so I have done some playing with wine reviews. And I was trying to see if wine reviews would cluster by wine type. It's really important to remove the name of the wine from that list. Because I wanted to see if they inherently clustered by wine type as opposed to having the word Cabernet in them or Pinot Grigio. So it's really important to remove that. So that's a situation where I explicitly added every single name of wine that I could think of to the stop list to try to remove all of them. So there's other examples where I think there was a study, some researchers did a study on news groups, and they found all these clusters by user posts, but they realized they had left the email addresses in. And so it wasn't really that profound that they were clustering on the user's writing. They were clustering based on the email address presence. So those are all situations where you have to be really mindful of the data and mindful of your stop words.
Did the wine cluster?
The wine clustered very well, yes. Sometimes there was one situation where they clustered by wine reviewer. I guess this person just had a very unique flair on how they write their wine reviews. But they did not cluster based on the presence of the name, which was the important part. Yep.
So we were looking at a CSV file for this demo.
Mm-hmm.
What other file types can you get more specific, industry-specific, like CAD files, like PDFs?
So with like PDFs, you said? Yeah. So reading those can definitely be done. You need additional libraries to extract text from PDFs. It's a really common task, though. So if the PDF has text embedded in it, it's not as difficult. If it doesn't have the text embedded in it, so sometimes really old ones or scanned files haven't been converted. So then you would have to do something like OCR, which is optical character recognition. That has challenges because OCR isn't perfect. So you effectively introduce misspellings. If there's columns in your data, so I have a friend who works for a scientific publishing company, those things are challenging because then you have discontinuities. If it's a science paper, what do you do with figure captions? Yeah, so there's definitely lots of ways to read other things, yeah.
Database one?
Oh yeah, so if you're using Python, just taking what we're using here, you can connect to SQL, a whole variety of databases, Mongo with Python. So yeah, there's connectors for lots and lots of things. Good question. Was there another question? Okay.
Do you ever pre-process by pulling out how many nouns and what verbs depending on the sector you're looking at?
If I think that those are really important features for what I'm doing, you could pull them out and probably even specifically encode them as a feature. So taking my New York example, if you didn't want to do bigrams, for example, you could pull out just any occurrence of New York and literally add that as a column to the count vectorized matrix, to the document term matrix that we made, and make it a feature. And then you can custom weight it too. So if you think that's really important, you can upweight it. Okay, so nearing the end. So we took our lemmatized input and created a count vectorizer matrix. And so we can see there's 5,572 documents, and our features are at 6,528. And these are just SMS messages. These are just text messages. So you can see, I think, pretty easily how this can really expand. And so the maximum word count for any value in this matrix is 18. So there's somewhere a word that appears 18 times in a single text message. I'm not even sure what that would be. I had to look that up. Okay, so this is mostly zeros, but you can see the matrix itself. Here's one encoded where binary has been set to true, and then the n-grams have been set. So we'll pick up n-grams of length 1 and 2. So here it blows up from 6,000 some features to 35,000 features, just by doing unigrams and bigrams. And here you can start to see we have so many features that, this is binary, but we have so many features that it's really starting to take up a lot of memory if you can measure the memory for things like this. And so that's it. Point I simply wanted to make, careful with n-grams. Any questions? Yes?
Can you touch on the count vectorizer and the fit transform again and exactly what that's doing?
Yep. So we'll go into that a little bit more with machine learning, but that's okay. No, I'm happy to answer that. So when we do machine learning models, we will end up dividing our data into train and test sets. So we want to make sure when we train our machine learning model that we're not biasing it against the natural noise of the data. We don't want to fit noise into our model because it doesn't really describe a trend that we can predict. So normally when you use count vectorizer with your training data, you'll do fit and then transform, and you'll do separately on the test data just a fit, or just a transform, excuse me. Don't do fit. Does that make sense? So you only want to do the fitting on the training part of the data.
So it essentially just partitions it.
Mm-hmm. And you can do them separately. So on the training data, you could do .fit, and then you could do .transform. It's just more convenient to do it in one. But then on the test, again, you'll only do transform there. No problem. Okay, I'm going to jump back to the presentation briefly. And do you guys want a quick break? We have coffee break in at 11:15, but do you guys want a quick 5-minute break? Yes? You want to keep going? Okay, no problem. The vote is in. Okay, so now that we've numerically encoded our data, it's the fun stuff. This is my favorite part, the machine learning part. So what is machine learning? It's couple of you have done it. What would you define as machine learning? Ignore my definition. You've done machine learning. I'm looking at you.
I don't know a formal definition, but when I think about machine learning, I do a lot of unsupervised learning. But in general, it's taking a bunch of data, running some sort of algorithm to figure out how to classify, cluster, regress, predict, and then using the model itself to then take a new set of data and then do some sort of prediction, classification, et cetera, without a priori specifying certain assumptions about the data.
Good. Yeah. Yeah. That's what I would say. It's easiest. I think it's easier to explain supervised machine learning, but we're trying to learn from our data, and so my background is as a scientist. A lot of times in my field, we knew the functions that were underlying the phenomenon that we observed. It was much simpler. The cool thing for me about machine learning is we don't know what the function is. We don't care sometimes. And even if we did want to find it, a lot of times it's too complicated to be able to figure it out. So we just say, you know what? I'll give you some features, machine learning method, you figure it out, you learn, and then you can get an answer. So that for me is what I think is the really cool part of machine learning.
So, how much do you know into all the algorithms that you typically use?
So we're not going to cover them in depth today, unfortunately. But when we teach like the boot camp and we do corporate training, we go into them quite extensively. So yeah, and I'm happy to answer questions. I just spare you 3 weeks of our boot camp.
Just a general question, going off of his definition. So machine learning is sort of a way of deriving a function from a known data set. And so going back to sort of where from an academic's what were the tool sets that you used then that sort of kind of matured and grown in this machine learning space?
So I think there's still room for a lot of types of regression. We use them regularly in machine learning, linear and logistic regression, the former to predict numerical values, the latter to predict binary outcomes or probability outcomes, if you will, either way. So those, I would say, have matured a lot. One that's maybe a little less common is nonlinear least squares regression. So that's something that I used to use. I use a little bit less. But that's in part because machine learning is so powerful, you would just use that these days instead of a nonlinear least squares regression. So I think some have matured. So the linear regression has really progressed a lot. But I would say others are used less frequently because with machine learning, there's things that work better. So. So we sort of touched on this, but there are two types of machine learning data, and we have sort of material and exercises to cover both. The first is supervised machine learning. So the data points have a known outcome. They have a label. So we saw that with the spam data. There was spam and ham. And so when we work with a set of data upon which we're training our model, we give them those labels. So the machine learning algorithm says, I see these features, I see these labels, I'm going to try and make them all, I'm going to try to fit my model parameters so that I can come out with the correct outcome. And then you feed it a new set of data and try to predict and measure how well you do. So that's sort of the gist of supervised machine learning. There's regression where we're predicting a continuous value. So linear regression, for example, is common. And there's classification where we're predicting either a binary outcome or multiple categories. So types of cat versus dog is sort of a binary outcome. Types of irises. There's a very famous data set we'll cover that's 3 different species of irises. So that's commonly done. With unsupervised machine learning, there's a lot of unsupervised machine learning in text. And there, instead of having a label we're trying to get our model to fit to, we're trying to find an unknown set of structure in the data. So a common occurrence in the business world is customer segmentation. So you don't know how your customers fall, but maybe you try to do some clustering. That's an unsupervised machine learning method. And say, I can sort of see my customers fall into this many groups. Or maybe you're a clothing company and you want to understand your customers and you have a set number of clothing sizes. So then you can try to fit that to understand the structure. So a little bit of vocabulary before we begin. So with supervised machine learning, I like the spreadsheet model. So you can sort of think about your data, where each data entry is a single row in this spreadsheet. And so the vertical columns are features. And so in this case, we have something called sepal length, sepal width, petal length, and petal width. These are features of an iris flower. So this is a famous data set. And then we have each row, as I said, is a data point. So this is a single observation. And then finally, the labels. So again, with supervised machine learning, this is what we train our model to predict. And then when we see new data, we want to try to predict. So there's 3 different types, 3 different species of irises here. So Virginica, Setosa, and what was the Versicolor is the other one. All right, so we've talked about features here, and this is pretty obvious, the numerical values that are the length and size of these features. But what are the text features? And so we've gone into this. The tokenized words, the n-grams, parts of speech tagging if you use it, chunking of sentences, and if you find a way to encode syntactic structure, that's another way that you can create features. So with supervised machine learning, text classification, we want to predict a categorical variable. So if an email or a text message is spam or not. So you use that probably every day when you check your email. You have a little spam filter going on in the background. That's what it's doing. So given your X data, the email text, tell me if this is spam, file it in the right folder, or whatever. And so then our goal is to build a machine learning model that predicts if a new email is actually spam or not. And so for classification, there are a lot of methods that one can use for predicting an outcome. And so these are, the ones I've listed here are all encoded in scikit-learn, which you have installed with Conda. That's the same library from which we used Count Vectorizer. So logistic regression is sort of what I call the workhorse. It fits a very simplistic model. It often works really well. It's not a big model to store in memory. So we'll be using logistic regression. But if you have experience with other machine learning methods and want to try those instead, that's totally fine too. Naive Bayes is commonly used with text. SVM, support vector machines, sometimes is used. Random forest and boosting are really powerful methods. I generally tend to use them less with text data. So I'm happy to answer any questions about these, but I'm not going to go into them in depth. OK, so we're going to build a machine learning model to classify spam. So we have this data that we've already done pre-processing on. And it's labeled as spam or not. And we want to process it. So all of the pre-processing steps that we've already gone through will be done. And they'll actually be done for you. And we'll use this numerical data set then to put it into a machine learning classification algorithm. And so then given a new set of data, process it the same way and see how accurately our model predicts. So we'll do a quick walkthrough. And in the classification walkthrough, we're going to do some numerical data. So that iris data set that I showed you is built into scikit-learn. And we'll walk through how to do that. And then the exercises will be text classification on the spam set that you have already. So let me switch over. So if you load in your notebook exercise walkthrough 3. There. All right, so I just have some simple imports set up, and we'll load then the iris data. So this is built in, as I said, to scikit-learn. And we can put it in a data frame. And so just like you saw in the presentation, there are columns. And this is just the X data, so these are just the features. Sepal length, width, petal length, and width. And then the Y data, the Y variable contains the species. And I've only printed a couple of them here. So we'll be using our X and our Y effectively to build a machine learning model. And so I alluded to this earlier. With machine learning, we want to make sure that we're not fitting the model to the noise in our data, because that's not really a fundamental part of the function that we're trying to approximate with machine learning. So to do that, we take and hide a part of our data from the model. We never show it to the machine learning model. And then we fit it, the model, on the remaining part of that data, and then we use that hidden data to see how well our model does. So there's something in scikit-learn called a train-test split. So train is where we train our data. Test is where we test how accurate the model is. And so we'll end up with 4 variables from this. We'll end up with our X, train and test, and then our Y, train and test. And so this will split everything for us. So sklearn has, as I said, lots of classification models. So this one is logistic regression. We can import it. It's anytime you see capital letters like this, it means it's a class. So we create an instance of it just called LR. And then very simply, to fit the data, it's lr.fit. So it's kind of like count vectorizer.fit. In this case, we have to give it an X and a Y, as opposed to count vectorizer, where we just gave it our text data. So this fits the model for us. And then we will measure the accuracy. And so we take our fitted model, LR, and we do predict. And we just give it the X test data this time. And so we can store those predicted values and then compare them to the real values, to the test data. And so accuracy score is a function that will give us that result. sklearn has something called a confusion matrix. It's a common matrix used in machine learning. So the rows represent the actual values of the inputs, and then the columns correspond to the same set of species and what they were actually predicted. So what we're going for with the confusion matrix is, in an ideal world, to have only numbers on our diagonal. Any off-diagonal element is a misclassification. And so I have a plot that I think makes it a little bit easier to see and to understand. So you can see we have one misclassification. It was a versicolor that we classified as virginica. Yep.
How do you choose your penalty method? Like you use, right now it's default to L2 regularization.
Mm-hmm.
Switching to L1 when I ran to improve the accuracy. When you're going through that, do you just test and see, or is there a method, general method that you use?
Right. So regularizers help deal with situations where you have too many features. Oftentimes it's empirical. So they work differently. L2 will penalize the errors by the square value. So it'll take all of your parameters and sort of penalize them evenly. L1 does, yep, it'll throw some out. Often it's empirical. I used to do research, and I developed some machine learning methods that were based on L1, so I'm a little partial to L1. The downside to L1 is that it's a little bit slower to fit, not here per se, because this is a small set, but when you get to bigger data sets, the way the search function tries to converge with L1, it's more challenging because it's an absolute value and it's not differentiable everywhere. So you know that. But I have a sort of a soft spot for L1. Yep.
So in the confusion matrix,
Mm-hmm.
can you explain, the one is saying we predicted versicolor, but we got its actual virginica?
I think it's the other way around. I'd have to see how I set it up in the graph, but I think it's versicolor that's predicted as virginica. We could probably tell. All right, that's not going to be fast. I was going to check. You can see which is missing one, but I think it's versicolor that's predicted as virginica, because I think there's 13 of each in the iris. Okay, one last thing that we can look up. So there's lots of error metrics with scikit-learn. Accuracy is one we've talked about. Accuracy is simply how many did you get right for each class. There's other types of methods. Well, actually, so the answer to that question is up there. I said it correctly. There's 13 of versicolor and 13 for Janica. But there's other error metrics. We're not going to cover them. They are sometimes important. Accuracy isn't the only metric. If you have a medical diagnostic, you probably want to make sure that you catch everyone as potentially having a disease, as opposed to missing some people, for example, if it's an early stage diagnostic. So there's different error metrics that you would use there. Conversely, if you're predicting stocks, you really don't want to predict any duds, so you're okay missing some. Different types of error metrics. So let's jump over to our text classification. This is notebook 4. And let me zoom in a bit. So I have set up for you the pre-processing of the text data. That's done in the second cell. My computer is slow. Okay, so that does all of the pre-processing, stop words, etc., that you need to do for the machine learning part. And then the next cell will split the data into an X and a Y. So X is the features, and Y is the labels that we're going to predict. So the next 4 questions, actually don't answer question 4 yet. The next 3 questions are left up to you to answer. And so I'll circulate. I think there was one person who had some problems, and I'm going to come try to talk to you. But then I will be happy to answer questions. You can do that. It does count vectorizer on your training data. And that's not such a big deal with count vectorizer because it doesn't do any normalization of your data. But if you fed it to TF-IDF, where it does, it looks at the whole corpus for documents to normalize it, then I would say that's overfitting your data. So yeah, as a habit, I don't do that. And as a habit, I tell the bootcamp students not to do. But it's fine with count vectorizer. You will end up with extra features in your corpus if there's words in your test set that are not in your training set. Do you think that's overfitting? Maybe.
You won't have an issue with the number of features you different?
Well, so yeah, the number of features, if there's words in the training set that are not in the test set, yeah, there will be different features. Is that overfitting? I would say that's a little less definitively overfitting than if you do TF-IDF, where it's actually normalizing across an entire column. But yeah, you can end up with different features because there's words in your test set that just effectively get ignored if they don't show up in the training set. So.
If you did that, when you do the logistic regressions, it would be ignored in your test set because they're not in the training set.
Right. They don't get numerically encoded. Yeah. Yep. So yeah, as a habit, I tell, when I teach machine learning, I say do it first. Count vectorizer, maybe not so bad, but TF-IDF is definitely a no-no, I would say. It can become kind of insidious, when's the right time to do things sometimes. I don't think it's always as clear-cut as we might like it to be. So train, test, split, and then I did a very simple count vectorizer model for the first one. And you can see 5,482 features. The second one, I have this habit of doing for the second one binary and then unigrams and n-grams. You can do whatever you want. So again, feature space gets quite a bit larger, 26,800 some features. So logistic regression, there's actually 2 forms of logistic regression in sklearn. So the one I showed you earlier, which is totally fine to have used, is regular logistic regression. There's also a logistic regression CV. Does anyone know what the CV is? Cross-validation, yeah. So there was a question earlier about a regularizer, which helps deal with too many features. Cross-validation will try to find the best parameters for the regularizer. The regular logistic regression function will take whatever you give it or the defaults. So the cross-validation one will take a little bit longer to fit because it's trying different values for this method called regularization that helps deal with extra features. So just an FYI. But either was fine. We're just learning. So this is, the C's are a parameter for this regularizer that I was talking about. And it further subdivides the data to try to find this best parameter for the regularizer, and that's called cross-validation. So we fit our model and predict the outcome. So again, just a very friendly reminder, you fit on the training data, predict on the test data. And so then these are the predicted values for spam and ham that we'll get out of that cross-validation model, or out of that logistic regression. Okay, the second one, very similar, fit and transform. Again, this one will be bigger because it had unigrams and bigrams in it. And we can measure the accuracy against the ground truth, which is the Y test for each of the predicted arrays. And it's pretty similar. This is not such a challenging training set. We do a little bit better with the first one. You could probably try to tune that logistic regression model a little more, tune the regularizer, and you probably could do better. But usually that's good enough. And so one challenge with this data, I put this here just to make a point. A challenge with machine learning supervised methods is when there is an imbalance in the classes. And so the spam here is much smaller than the ham. Logistic regression is kind of so-so on class imbalances. There's other methods that might do better on class imbalances.
Can't you just duplicate the ham?
You
Spam, sorry.
You can upsample. So you can try to deal with your data beforehand by balancing the classes. You can either throw away some of the ham, or you can upsample some of the spam.
When your classifier says that the accuracy is at 97, but it's inherent.
Right, right, right,
It's gonna be like 80%.
right. So that's why I made a point of plotting the confusion matrix. I would say upsampling is a little bit more complicated when you're dealing with text data. When you're dealing with just numerical features, upsampling is not such a difficult thing. You can upsample based on the count vectorizer, probably. But yeah, those are all options. Question about?
You may have said this, but do any of these functions condition your X array in the situation that you've got a token only shows up at the same time as another token? So they're identical
So that would be probably, unless you built that in as a feature, like a bigram. The second one is a bigram. Is that what you were asking?
No, meaning that won't you end up with a degenerate set of solutions if you've got two tokens that are always co-occurring?
Collinearity, yeah, you could deal with that. It doesn't deal with it right now. But there's ways to try and find those features and throw them out mathematically. The other thing, regularization will try to deal with some of those. I would say L1, in my experience, is better at dealing with multicollinearity. It will effectively just set one of those tokens to 0. It goes and figures out which features you actually really need to be there. So you could probably get it to work with L1 without doing it manually. Okay, and so we see, as a friendly reminder of the class imbalance, we kind of don't do so well. We're missing 32. But we actually do a little worse with our more sophisticated bigram model. I would probably go back and try to do regularization with L1 on this. If I were going to try to improve this further, I would also probably try some other methods that do a little better on class imbalances.
How would that improve it?
Well, so L1, there's probably, I bet that this bigram model will do better if you get rid of some of the data. Like you can keep only the columns, the features that matter. And a regularization that uses L1 will do that better than the default one that we're using. So has anyone used naive Bayes before? Yep. So it's commonly used with text data. It's nice because it's a really simple model. It's not a lot of values to store in memory when you are trying to fit data. So it's commonly used with texts. If you use a binary data, you want to use a Bernoulli naive Bayes, which uses a Bernoulli distribution. If it's count data where it's greater than 1, you'd want to use multinomial. If for some reason you were doing continuous values, like with TF-IDF, you'd want to use Gaussian naive Bayes. So different types of naive Bayes. So I fit 2 of these, and one of these was with the binary data. The second one was, that's why I used Bernoulli. And I measured the accuracy. They don't do a whole lot better. In fact, on the logistic regression for the first one, it does exactly the same. There's a little bit of difference on the second one. And logistic regression does better. So question 4 is after we do the TF-IDF section, which is really short. It's 5 minutes before coffee break. Do you want to do the slides for TF-IDF, or do you want to just do your coffee break? Slides? OK. There's only a couple. So I can easily get that done in 5 minutes. Let me switch this over.
Have you done much with using like the voting method across multiple algorithms?
So stacking?
Yeah.
Stacking methods together. We do it a little bit in the boot camp. I don't tend to do it with text data. Often it will do better. It's more parameters to store, more models to train.
Yeah.
Technically you need to split your data yet again so that you're not overtraining. So, but it's something you can try. It's kind of cool thing about machine learning, or the challenge and cool thing about machine learning is that it's so empirical you can just kind of keep trying things. So going beyond count vectorizer, there's problems sometimes with either using binary or word count values. Binary is really simplistic. Conversely, with word counts, if you have a word that appears very commonly, it can dominate your model. So particularly when you start dealing with long documents, if they have a word repeated a lot, it doesn't necessarily add meaning to your model or meaning to your machine learning model. In fact, sometimes the more rare words may be of interest. They're used less frequently. So how to deal with that? When we want a metric maybe that goes beyond count vectorizer. And so there's 2 concepts that are related that we'll introduce to talk about the alternative. The first one is term frequency. So this is an alternative to using binary or counts. We simply balance the count of the word in a given document with a log transformation. This is really commonly used in machine learning, also with linear regression, when there's skew to the right. So if you look at page clicks, there's the joke, the long tail of the internet. It will be a lot of pages with a very few number of clicks, and then it trails off quite aggressively. That's typically done with treated with a log transform. The 1 is added simply to avoid taking the log of 0. So anything that's a 0 will just get a 1. So that's term frequency. So we can use this to deal with the situation within a single document where there's lots of counts of a word, and we don't want it to be so aggressively weighted. But the second question arises then, what about words that appear across multiple documents versus a word that appears in maybe just one document? What do you think about that? Maybe the rare words are more important. So we dealt with sort of the horizontal, if you think of the count vectorizer model. But there's the vertical situation too. Maybe words that appear rarely are more important. So that's called inverse document frequency. And it's again a log transform, and we simply weight the total number of documents, so that's on the top, over the documents containing a given word. So that value it's a smooth decaying function, and when lots of documents contain a word, we downweight things. So term frequency, inverse document frequency. So that's what TF-IDF stands for. Those two things, usually we multiply those two values together, and it gives us TF-IDF. And we are right on 11:15, right on time. So there was one question 4 in the previous set of exercises that used TF-IDF. So we'll do the coffee break, and maybe 5 or so minutes after the coffee break's over, we can talk about that one, and then move on to clustering. So for those who finished, whose TF-IDF model did better? Yeah, mine did too. Sometimes that happens, sometimes it's not. In this case, with the spam data, I would say a lot of the words are very similar. So that might be why TF-IDF does better. Words are similar across the different documents. So that would be my first guess. But machine learning is empirical, as I like to say. So if you jump over to the answers for exercise set 4, so I fit 2 models with TF-IDF. The first one was just with the default set of features, and in both cases, I had better results than with count vectorizer. This was sort of 98%. Again, with a skewed data set, you always want to be careful with accuracy, though that's what we were using here. In the second set, I turned off use IDF. So that was the second term we talked about with TF-IDF. So this is not adjusting the weight across documents anymore. It's only adjusting the weight within a given document for word frequency. And that one did even better. So caveat emptor, you could delve into this more and look at a confusion matrix if you wanted to decide if that was really the result that you wanted. Any questions on that before we move on to clustering? Everyone's good? Okay. So who's done clustering before? A bunch of you, I bet. What kinds of clustering algorithms have you used? K-means? K-means is, and what else? Okay, yep. Popular ones. Yep. It's related to LDA, so, yep. 2? Yep, you said you were interested in topic modeling a lot, I think. Yep, so we'll do that actually next, shortly after this one. So clustering. So if we take a data set, and here we have plotted on the x-axis income, and then age, so maybe this is customer segmentation data. To begin clustering, we find 2 sets of the 2 data points that are very close together. And so we can group those and color them green in this case. And then we find the next 2 closest pairs of data and group them together. And then we keep going. And then we keep going again. And so eventually we get to the point where we are merging pairs of clusters together. And that's totally fine. Continue on till we have lots of clusters. And now we're starting to merge the clusters together, and we're reducing the number of clusters that we have. Keep going. 4, 3, 2. And then if you kept going, we keep going forever. So this is a very specific type of clustering. It's a hierarchical clustering. So it creates a hierarchy when you start grouping the clusters together. There's other types of clustering that are not hierarchical. So when do we stop clustering? Who has an idea of when you would want to stop clustering? Any ideas? Sure, if it didn't change. So usually that is sort of if you get there's ways to measure distances between the clusters, and if you reach a set value, then oftentimes you would want to stop. Sometimes there's a correct number of clusters. So if this relates to something where there's a known number of customers, maybe then or customer segmentation, maybe then you would stop at a given number of clusters. Those are sort of usually the two, broadly speaking, metrics that you would want to use to decide clustering. So this is moving in the realm of unsupervised machine learning. So it sometimes is a challenge or an art, depending upon how you want to spin it, to decide when to stop and what the right number is. So I alluded to the second one with cluster linkage or distance. So there's a couple ways. Go ahead.
Is that within and between?
I'm sorry?
Is that within and between squared subs?
For cluster distance?
Yeah.
So there's different ways of measuring. We'll talk about two of them. There's actually lots of ways of measuring cluster distance. So great segue. So there's lots of ways of measuring cluster linkage and deciding when you've reached your threshold. Again, a lot of these tend to be empirical. Sometimes those of us who do this a lot have a favorite, and we just pick the favorite too, to be frank. So you can measure single linkage, and so this is just the minimum pairwise distance between clusters. So for the entire cluster, where are the two pieces of data that are closest to each other? And so you can see two examples, but you can build in the rest of them as well. There's average, where we effectively take an average of all the data points to find the center and then measure those distances. You can add more. Oops, I didn't mean to hit the second one. The last one, and I tend to use this one a lot, it's called ward. It merges cluster based on how dense the clusters are before and after merging. That's called inertia. It's basically the variance of the cluster. So we have to measure these distance between the observations. And the choice of what this distance value is also a parameter that we have to decide how to treat when we're doing unsupervised machine learning models. So we talked about the ways to measure the cluster distance, so average, single, ward. But what that value is also something that has to be empirically determined. So if we take two of our data points, so income and age, and we're only showing two of all of them, a common way of measuring that distance is the Euclidean distance. So this is a standard measurement. We're measuring d, the diagonal here, and so you square the two distances and then take the square root. That's the Euclidean distance. The second one is called a cosine distance, and we are effectively measuring the angle between these two pairs of data points. So cosine distance is a little bit more commonly used with text, and the reason for that is that the distance from the axis or from the origin doesn't matter. So this distance is effectively the same as this distance. Anybody have an idea of why that's often used with text? Pretty close. There's a lot of repeated words. So if you have two different documents and you have a shorter document that says hi, you, and hi, but you have a longer document that says all of the same words, just repeated, sort of intuitively, those probably aren't that much different, right? So you'd want them to have a very small distance between the two of them. So cosine distance is a great way to do that. These
X and Y there, count?
I'm sorry?
What's your X and Y on that?
Yeah, it's count of you and count of each word. Sorry, thank you. Yes, so if the ratio of hi and you sort of linearly increases about the same rate, then you would call the documents extremely similar. Does that make sense? Yep.
So in this example, you're using cosine similarity with count vectorizer. Would you ever use it with the t-fit?
So I tend to use it with count vectorizer. I've tried it and sometimes gotten better results. But there's a lot of sort of philosophical discussions to be had around that. But yeah, I tend to use it with count vectorizer. Intuitively, it makes more sense. To me, intuitively, TF-IDF makes more sense with Euclidean values because you get a continuous number. But yeah, I've known exceptions to that where it doesn't work as well. So the name of the game with clustering, and we'll do a walkthrough of a couple clustering methods here in just a second, is decide on a clustering method, decide on a metric, and when to stop, and then how to measure your distances. So these are all of the sort of empirical features that you can tune with clustering. And so we'll go to the next notebook, which is notebooks 5, and we'll do a walkthrough, and then we'll do some exercises together. Okay, so we'll go through a very simple example of clustering, and we're going to use SciPy, which is a library that's for generalized scientific computing, not maybe specific to machine learning, but it has some nice clustering methods in it. So we are going to make some fake data. Fake data is sometimes easy when you're trying to understand how something works. So we'll make 2 sets of clusters here, and I'm just giving them 2 features so that it's very easy to plot them and see the results. And we'll do center them at 2 different points in space. So we'll make a Gaussian cluster that's centered at the coordinates 1, 1, and then one that's centered at the coordinates 3, 1 in space. And we can plot the results and color them so that we know which set of clusters is associated with which data point. Yours may not look exactly like mine because they were made randomly. So I said pairwise, the way we calculate the distance metric is an important choice we have to make. So first we'll talk about, the first one is cosine similarity. So that measures the similarity via the angle in space. To get the distance from a cosine similarity, it's simply 1 minus that value. So we can take our data and feed it directly to this cosine similarity function from SciPy, or from sklearn, excuse me. And so then our distance cosine, and let's print that out. So we can get the pairwise distances from every point to every other point in our set of data. We can also do Euclidean distance. So this is the more standard distance that we talked about at the beginning. And so the type of clustering we went over, where you start with a single one and then certain sets of clusters tend to engulf other clusters, that's hierarchical clustering. So SciPy has a set of clustering methods that are hierarchical, and they use different types of linkages for how to determine the clusters. So average, which we talked about, that's where you calculate the center of each cluster and then measure the distance from that very center. There's also Ward, which measures the change in inertia. So it examines the variance change in the clusters before and after merging them as one. So we can calculate these 2 sets of linkages, and it'll make more sense when we plot it. So we'll use what's called a dendrogram to plot. Who's used dendrograms before? Fair number of you. I'm trained as a scientist, so I always thought dendrograms were for looking at like genetic variation in species, but it turns out that they have broader use than that. So a dendrogram helps examine how the species, if you read this from sort of right to left, because of the way I've plotted it, you can see how we start with a lot of clusters, and then they gradually merge together as you go from right to left, until at the end we're left with a single cluster, one giant cluster, which is the entire set of the data. And so here it found sort of 3 sets of clusters, and then there's one sort of lone one there at the end. And so really, the trick is deciding where you want to cut this in vertical space and the number of clusters that you end up with at the end. That's sort of the nuance with clustering. And so here's the dendrogram from the ward distance. This one looks a little different. We have a set of 3, and then they all merge at the end. So you can decide where you want to cut this. If you say, I want 3 groups, then you can get the assignments of each of your data points by using what's called F-cluster. It means flattened cluster. So if you want to slice it with 3, it'll find the sort of longest distance you can go and still have 3 clusters left. And so you can use F-cluster to do that. And so here I said 2. So it's going to slice things somewhere around in here where there's 2 left. Yep.
Would there be a reason why you wouldn't look for the maximum where you still have the same number of clusters?
Sure. If you're doing customer segmentation and you know that you have a limited number of segments you can address, or if you're, I kind of like the clothing size company, the clothing size example. Say you have 5 different sizes of clothes. You want to decide if there's differences in your customers with those sizes, then you pick it at 5. So sometimes the problem has a value that you pick. Sometimes it doesn't. Sometimes you just look at how the numbers sort of change. There's lots of metrics to examine clusters and their density and the way in which they relate to each other. And so if you don't have a specific K, then sometimes you have to look at those. It's definitely more nebulous than I think a lot of people would like. But you don't necessarily want the most number of clusters. Does that make sense? So here we're cutting it at 2, but you could cut it at 3 if you wanted to also. And then we can plot. So I plotted with different shapes. So the colors correspond to how the data was originally assigned from 2 different clusters. And you can see the shapes correspond to how the data ended up being classified or ended up being assigned to a cluster. So it's not always a one-to-one. And again, I want to stress this is not necessarily a supervised problem. So we didn't know that to begin with. But I think it's interesting to see that, yes, we made 2 groups of data, but things don't necessarily net out the way we thought they would. So there, it's obviously different this time because I'm working with random data. But things don't always net out the way we thought they would with clustering, which is important. So we'll do 15 or 20 minutes to see how we're doing. The next notebook, notebook 6, is some exercises to try for hierarchical clustering. And we will use a set of text data. This is Reuters. So it's a collection, it's a very large collection of newswire articles. We're only using a small bit of it. And it comes from a specific date, April 7th, 1987, if you want to be really precise. So the first couple cells will load everything that's necessary and read in the Reuters data. And I did all of the cleaning for you. And we're going to just pick from these articles. There's different topics that are known. So I picked 2. I picked cocoa and I picked coffee. So 2 things that I like to narrow down the data. And so the first question is you can use the pre-processing function that I created to process the data. That was also done in notebook, I think, 4, if you want to look back. And so we have our data frame. And we've selected cocoa and coffee as the topics we're interested in. So the first one was pre-processing the data with an automated function, and then running count vectorizer to create a document term matrix. So that'll take a second to run. And then let me make it a little bit bigger also. So here's our count vectorizer matrix that will fit on this data. So this is unsupervised machine learning. Just one second. So we don't do train and test splits here. There's not a ground truth that we know of. Does that make sense? What was your question?
When we first used count vectorizer,
Mhm.
we got a binary 0 or 1 of whether the token had ever occurred. Was that just happened to be the data set only had? Okay, so
Yeah.
in general, you do.
It'll do counts, yeah. That was the spam data, and so it only showed part of the, I think only showed part of it, and so you only saw like zeros and maybe a 1, yeah.
When you say you don't use a training or cross-validation for clustering,
Um,
sometimes you want to see a stable cluster.
You could do cross-validation there. I suppose if you wanted to compare how clustering works on different sets of data. But my point was that there's not really like a test split where we're trying to measure accuracy. So then we can import some of the SciPy functions we talked about, Ward and dendrogram and F-cluster. And then also sklearn has our cosine similarity. And you could have used Euclidean distance. I just used cosine similarity. So calculate that. We get a linkage matrix. There's a dendrogram. If we went and wanted to really examine things, you can take and pull out the labels or some sort of like the title string from your Reuters articles and examine where they lie in those sets of clusters. And I've sort of cheated because I knew that we took articles on cocoa and coffee. So I decided I wanted to sort of shoehorn this into 2 clusters. Again, sometimes the problem has a K, a value of clusters. Sometimes it doesn't. And we can look at the data itself and see that the first one is all about cocoa. Lots and lots of cocoa. So as one might expect, things clustered pretty well into where we thought they should go. And the last one worked similarly for coffee. There's more coffee articles. But you can see hints of coffee everywhere in there. So and there is one that looks like it's about lots of things. So I see tea and cocoa there. So that one probably can end up a number of places depending upon how you do your clustering, I would bet.
And this is disjoint when you do the topics?
It's what?
Will this be disjoint, so if it's in one topic, it won't be
Yeah.
in the other?
Yeah, the F cluster flattens it, and it can't be in multiple clusters at once. There's other ways of doing it where they can belong to multiple. I mean, topic modeling can kind of get into that. So we're going to move on to that next. So, yep.
In question 2, why do you only look at the first 25?
Because it's just simplicity. You could look at all of them. It'll take longer to run. There'll be a lot more clusters, but there's nothing wrong with doing that. I just picked a few to keep things short and simple. That's all. So everyone good on that? We can move on then to LDA. Let me do the switcheroo. So who's used topic modeling? 1, 2, 3, 4, 5, 6, 7, 8. So a few of you. I love topic modeling. I think it's pretty cool. So this is where there was a question earlier about, are these clusters, when we were doing the previous exercise, are they disjoint from each other? That type of clustering is. An article can't belong to 2 clusters. So it picks the best one according to whatever distance metrics you use. That obviously doesn't really reflect reality. Lots of times there's multiple topics in an article, or sometimes articles contain different fractions of a topic. They may be more about cars, but a little bit about, I don't know, wheels or something like that, tires, if you will. So the goal of topic modeling is to discover topics in a large collection of documents. So if you look at a news site, if you look at Google News and you click on topics, you drill down, you can find example articles that Google thinks you might be interested in. And if you happen to find 2 topics that are related, in theory, you could find the same article in the same topic set. That probably won't happen, but it's possible. So how do we do this in a way that really reflects the variety and the overlapping content of articles? So we can assume that the document is a distribution of topics. So say 30% business, 30% tech, maybe 40% science. So maybe it's about the pharma company or something like that. And we try to use that to discover structure in the article. So if we say this document is a distribution over words, this topic is a distribution over words. And so for all of the words in this topic, there's sort of a frequency with which they occur. So topic 1 here is about sports. It's got the words game and team and hockey. Topic 2 may have these words, but they're probably going to be a lot less frequent. So for topic 2, we see things like space and NASA. So it's probably about the space exploration. Topic 3, drive, card, system, SCSI, probably about computers. Again, words can belong to multiple topics, but usually they tend to have varying probabilities within that given topic. So knowing this topic distribution, we then examine a document and try to fit to that document a topic distribution. And we use the words in that document. So we basically try to sum up all the frequencies of the words in the document and find some combination of topics that fit. So it's kind of, that's what topic modeling is. It goes by another name when it was developed. There's a couple ways to do it, but the main one that we're going to talk about is latent Dirichlet allocation, or LDA. So this is a specific, it's a generative model. So it tries to imitate the way that the data is generated. So it tries to imitate and understand what those topics are in the document that created the words of the document. And so we assume that the set of topics is shared, and to create a document, we generate a topic, and then we generate a word from that topic. And we move on further in the document, and further and further. And so what you'll get out of LDA is a distribution of topics. And so then we assume then a set of documents. For each of those documents, they were created in this way. And so how do we figure out what those topics are? We reverse the process. We won't specifically go into the math, but we will do some examples in Python together. So let's jump to that. It's just one notebook this time. There's sort of a walkthrough, a really cool visualization, and then at the end, there's one question of sort of repeating the topic modeling for the data that we're going to load in. And so this is notebook number 7. So we're going to be using some news group data. So this is from ye olden days of the internet. People used to post in news groups. Not so common anymore. I have to explain to some of the students in the boot camp what a news group is. All right, so we'll load a couple of topics from this news group data set. So there's 20 news groups, and we'll load 5 of them just to keep things manageable with our modeling. We'll load sci space, so space, Mac hardware, autos, baseball, and science and medicine. So we'll fetch those and see how much data we have. So it should be just under 3,000 documents. And again, we can take and process the data using our handy function and create a data frame. It takes it a minute. This is a decent amount of data. And lemmatization is slow. Okay, so it's all cleaned. So the next part is our old friend, count vectorizer. We're going to create some numerical features. This time I pegged the number of features at 1,000. And you can just feed that to count vectorizer. You can set the minimum occurrence of a particular word in documents. So we're ignoring words that appear fewer than 2% of the time, and we're ignoring words that appear greater than 95% of the time. Oh, the min number of documents. I read it wrong. So we're ignoring words, thank you, that only appear in 2 or fewer documents. Thank you. Yep.
When you set the number of features,
Uh-huh.
do you know the decision model for which ones you include and which ones it doesn't?
You can get them after the fact. You won't know what ones it picks out. So with count vectorizer, I do believe it picks the ones that are most frequent. Yeah. Whoops. So there are multiple libraries that have LDA implementations. One of them I was going to have you use, and then there were some challenges with installing the LDA library. But we'll use the one in sklearn, which should be installed. There's other ways to do topic modeling, and there's other related methods. I know someone mentioned that they use NMF, non-negative matrix factorization. So this is effectively a matrix factorization problem. Just know that LDA isn't the only way to do it. And I cheated, well, I don't know if I cheated, but I gave it the number of topics that I wanted it to fit to based on the data that we selected from the Reuters. So we selected 5 topics, so I gave it 5 topics to fit. And so that'll take just a second. And we can look at the top words that are associated with each of these topics.
Can you say again what tells it to choose 5 topics?
Yep. So I set n topics by the length of it. There's topic list is what I gave the Reuters loading function. And then within the LDA model, there's the n topics equals n topics. So that's how you limit it. All right, so we can print our top 20 words. And for the first one, it's a little bit difficult. Something about, I see food. For the second one, we can tell it's sports. For the third one, health, medical. That was our science med topic, probably. For the fourth one, I see Apple. So I'm going to guess that Mac. That was probably our computer group. And the last one, NASA, satellite, system, orbit, probably our group about space. And then we can visualize the topic model. This is the library PyLDAViz that many of you were downloading. So if you run this, I love this library. So it lets you visualize your topic model. And a lot of it's a little bit esoteric, but you can mouse over the topic. And so when we printed the words out previously as text, you can see them on the right. So for topic 1, we can see the words, and the blue bars are their term frequency in the entire model, and the red ones are just within this topic. So you can things like car, drive, you can see Mac in topic 1. Topic 2, I think this ends up, it didn't call the topic numbers the same thing, but this ends up being the topic that's a little bit esoteric, I think. And then you can move over to topic 3. And we can see this is our NASA one, so we can see space way up there. Almost all the occurrences of space are in this topic. NASA, launch, satellite system. So 4 different topics. This one was the sports one. You can see the team. And lastly, this was our medical one. So you can see the medical related terms. There's other ways you can tinker around with this. You can So this is small enough that you can select a threshold for what data points you see in the data. You can move through topics. It's really a nice visualization. I think it's fun to tinker through. Yep.
Do you specify somewhere what the multi-dimensional scaling method is?
I have never messed with it. I think you can, the way it does the reduction. It would be in, so there's other ways of doing LDA models, like there's a library called GenSim. You can give this GenSim models as well. I don't know if you can tell how it does the embedding. Yeah, I don't think you can give it the embedding, the different types of embedding. I think it just does MDS. Get over to close the window. So the one exercise in here is to try and fit a different number of topics, compare the 20 words. You can play with the model if you want a little bit, but that's just the one question. Yes?
Can you give me an example when you would a priori know the number of topics? I mean, the example you started with was Google News, and
Right.
On any given day you wouldn't know what's going to be in the news, right?
Right. Right. So you don't usually know the number of topics, I would say. It's something that you would work through in your model. In this case, we kind of did because I picked them just to reduce the size of the data set we were importing. But you wouldn't necessarily know. Yes, Jonathan?
I can give an example. So I did some internal data science work with a consulting firm, and they do assessments for other consultants. And they have a quantified score, and they also have some text, unstructured text, basically people's comments about them. And they're in like 5 or 6 different categories, but they're all wrapped together. They're not separated in different sections. So in that case, it's sort of like K-means, where you could say, I want to go for 6 topics, 6 bins.
Okay.
And hopefully, each of the topics is going to have the majority, those subtopics is going to have a majority thread that's along the lines of what we're looking to separate.
That's a good one. Yeah. So hopefully it sorts itself out in the end with that set of topics.
Yeah. It's not gonna fall perfectly.
Right.
But you could try to sort of tweak it up and down a few numbers and see if you can get them in the.
Get it. Yep. Yep.
Kind of like hierarchical clustering, that you need to really go back and say these clusters make sense to what I'm looking for.
Yeah.
Yeah.
It's very arts based.
Yeah. Yeah.
If
Yep.
you define goodness of fit or quality metric for
Mhm.
your cluster, like separation from other clusters,
Mhm.
of course you can do that search automatically.
Yep.
And there are generative models where you can set a prior on how many clusters you think there might be, sort of, or
Yeah,
simply
that's true.
a prior of, well, fewer is better.
Yeah.
And sort of use that as a way of automatically deriving a good number of clusters based on your prior. But in any case, you have to sort of say something about what you think is a good clustering.
Yeah. Yeah. Yep.
Another method I've seen is stability of the clusters.
Yep.
So running it multiple times on a random sample of
Mhm.
80%,
Mhm.
and seeing how much the topics change.
Right. So that's sort of like cross-validation, I would say. Yeah. You can look at stability of the clusters with sort of a cross-validation type method. You can look, there's other methods, there's silhouette analysis that you can use. That's commonly used with K-means, but you can look at that to examine how your clusters vary in space and density, et cetera. So,
Could
What's up?
you use the topics that you discover in the training set as features that you then see how the test set kind of maps to those?
yep.
How would you know, well, you don't know the topics, you don't know necessarily what the topics are. They just happen to be the ones you picked.
Right.
If you hadn't given us those lists, then we would have,
Right.
we would
But you,
have them anyways.
but if you wanted to do that, that's effectively using a cluster number. So you don't need to a priori know or assign a word to that topic. You can say, I want some features. I want to use K-means clustering. Or I want to use LDA, what cluster the article falls into. and use that as a feature. If you're trying to somehow feed that into a supervised model, you could definitely do that. That's done.
I guess I just don't, it's not intuitive how you would figure out, given how you would assign within the training and the test side, how would you,
Well,
what the probability of topics?
so as long as you have the same model that you fit on your test set of data, you can rerun how you did your clustering without fitting it. You can just transform your data, and you'll, based on the word numerical features, you'll end up with the same thing.
Yeah, okay.
So yeah, you don't, well, I guess my bigger point is you don't necessarily need to assign a word to the cluster. It can just be a cluster number. So.
Okay, thank you.
Mm-hmm.
One more quick question on the guidelines and setting the maximum iterations.
Mm-hmm.
You're using 5 here, and before was 10.
Mm-hmm.
What are the numbers that you normally use?
For here, I turned it down to make it go more quickly. I was using a bigger data set.
10 is enough to build a model on?
I would say that depends on your data. You could do something like you mentioned earlier, where you're using cross-validation to see how stable things are, and you evaluate on that. I would say that's not always clear from the get-go. And while we're working on questions, was anyone not able to download the fitted vectors for Word2Vec? I have some thumb drives if you want. If you didn't download the Google stuff. I don't see any hands. Okay. I'll have thumb drives to pass around. Yep.
I have a question for LBA. Are there certain types of data sets where that might not be appropriate? Like for this, we're using news articles, so most of them are pretty long. But I've played with it before with like Glassdoor reviews. I've noticed it seems like some topics, like Glassdoor or a lot of review sites, some people only write a sentence, others write 3 paragraphs.
Radically different.
Seems like for
Yeah.
your model, the topics might be biased towards whoever's writing the most.
Yeah,
Just looking at the distribution across all documents.
I would say that's very reasonable. And probably also when you're dealing with smaller things like a review, like you said, some people wrote 1 sentence. I don't think you're going to be able to get a very good distribution model built from that. So a joint distribution model.
Also, when you're dealing with those types of set, you can normalize on that.
Yeah, that's true. That's a good point. That's a good point. Okay, there's no obvious answer to that one. But I want to see if we've got sort of 15, 20 minutes. So we can do a little bit of Word2Vec if you want. And that'll be the final part. So I just have a few slides on that. Let me unmirror displays. All right, so Word2Vec, deep learning with text. So we've addressed this a little bit today, but the taxonomy, the size of the vocabulary of your matrix when you convert text into features can increase dramatically with document size. So there's a solution. It was developed at Google in about 2013, I believe, which is to use a very shallow neural network to create a numerical representation of each word. And so that neural network, the numerical features don't grow necessarily with the size of the document because we have ways to combine them together. So we can use these, this deep learning network to analyze our data, create numerical features from it, and then fit a model. So it's a simple way, extremely popular. I would say one challenge is that you need a lot of data to train this neural network. Fortunately, you can download pre-trained vectors and use that data. So Google provides theirs, which I had you download for this tutorial. Stanford, the NLP group, has their GLOVE vectors. You can train your own. If you have a very specific domain like medical knowledge or medical data, you may want to train your own. Google's generalized word vector may not do as well as you want it to. So let's talk about what this neural network tells us. It gives us an embedding of our words, of our sentences in sort of this big, large dimensional space. So it's called a vector space model. And we can use these vectors to understand the relationships between words. So some surprising things that came out when Google published this paper. The relationship between man and woman is very similar distance-wise. Again, talking about cosine distances we used earlier between king and queen. So sort of a fun thing that came out of this.
It's direction,
Yeah,
not distance.
it's cosine distance. I'm pretty sure. You can get a similar value with cosine distance. I'll show you in the tutorial. So the vectors can be embedded for each word to create an overall view of the document. So you can combine these vectors for a word you can sum them, you can average them to create a single vector for your document. And the number of features in your model or that come out of this neural network are effectively the features in your document, or in your matrix. So the first part, there's one notebook. It's notebook number 8. And there's a little bit of a walkthrough. And then we'll talk about how to fit a simple model with Word2Vec. So the second cell is going to take a little bit to load. It will load the Google Word2Vec file. And if you haven't already, in the Python file that's accessory functions that came with the notebooks, you'll have to give it a path to where the downloaded Google vector file is at. And so running the first 2 cells will load Google's models, or Google's Word2Vec model, and we can use it then to examine some word relationships, and we can do, again, feature generation based on text. So this model has a vocabulary. It's a dictionary, and it's quite large. As you can see, this one has 3 million words in it. And each word in this particular model has 300 features. So if we look at the word cat, and we also can look at those numbers, that's an array. And I think did I say cosine distance? I think and I meant similarity. Did I say cosine distance? Yeah, all right, you're right, I meant similarity. Sorry, it's been a long day. So we can see that cat end up the same. Cat and dog are pretty close, but cat and car are quite different.
Are there, I guess, other frameworks in how you develop new Word2Vec models for different formats?
So GenSim can definitely train one for you. I mean, they essentially use, like, I think, I don't know if you can adjust the neural network yourself, or if it's a standard, like the layers and the nodes per network are pretty standard. I've never trained one, but you can definitely train your own. So car, truck are more similar than car and drive. And so I mentioned this in the slides. We can examine the relationship between woman and man, and then king and queen will show up in our top words. It's taking a while. So queen shows up with most similar. Also in there, which makes sense, is monarch and princess.
Does GenSim assume a particular location for the Google Lens?
So that would have to be set in the file accessory functions. It doesn't assume any location because it doesn't come with GenSim. So this Python file is where it would have to be set. And you might have to restart your kernel after you change it. All right, so we can take a string. We can take breakfast, cereal, dinner, and lunch, and get the worst match, which is cereal. So let's talk about how to fit this as a model. Let's take our spam data set. Because it's small, it'll be relatively easy to deal with. Ooh, are you okay? Okay. And so we'll load it and process it. And we can make a train test split just like before. And you can use count vectorizer. You may want to use TF-IDF because what we're going to eventually get would be numerical features, or you can combine them. I was using it mainly to get the dictionary of words from this training set. So here's where we're going to get the word-to-vec vector for each word in the vocabulary. So this pulls out a list of all the words that are present. So we have simply a list of every word. That's present in our corpus. And then I made a dictionary, and I pulled out the words that appear in both our corpus and that are also present in Google's pre-trained model. So those are the only words for which we can create features, because otherwise we don't have a way of numerically encoding the features. And so one challenge or thing to overcome with Word2Vec is obviously the documents are different lengths. And so every word returns an array of 300 different values for this particular neural network. We need to find a way to combine those. Otherwise, we'll have different numbers of features because there's different numbers of words in a document. So one way to do that is to average them. There's other ways that they could be treated as well. But a simplistic way is to simply average them together. So this function that I wrote called embed words will go through all of the words in a given document and query the Google's Word2Vec model, store the array of 300 values, and then at the end, it averages everything together. So for each document, there is one array of 300 features. And that's what we'll use to train our model instead of TF-IDF or count vectorizer. Or you can take and combine them together and stack them together as both. So then you have even more features. So this will create the vector embeddings. So I underscored them with an embed. And then I had to do some finagling just to get everything into an array, a two-dimensional array, where the rows are the documents and the columns are the neural network generated features. So this will take just a second. We can see the train and test splits. Each of them has 300 columns, exactly like we would expect. And so I used those to create, I combined them together as well. So you could fit, like I said, a model on just the embedded values from the neural network that we created above, or you can stack them together and create a gigantic Frankenstein model that's combined together. So here's them stacked together. So the last question, and we have 5 minutes to go, is to try to fit different models with this data. And so if you want to use logistic regression, that's what I did, but there's other ways to tackle this. So, yes?
So I really like the example of now using word to vet for a supervised learning example, but is there a way to use it for, I guess, learning new terms? So let's say you're doing topic modeling.
Mm-hmm.
Would there be an opportunity to use word to vet models on top of the topic models to get better, I guess, tagging of the different clusters?
So I've not done that, but you could embed that and use it as a feature in topic modeling and try it. I haven't done that. You can cluster things though, so you should be able to do clustering with it. It'll give you continuous numbers instead of like counts,
Okay.
of course.
I think more so from the idea that I'm trying to, let's say I have a set of terms that I'm interested in,
Mm-hmm.
but I don't know if that set is exhaustive.
Mm-hmm.
I'm wanting to do term discovery within documents, be it patents or what have you. If I want to find related technology, for example.
Mm-hmm.
I don't know that full list of related technologies. Could you use words of that in that example? Could you imagine a way in which you could?
You could look for features that are similar to words that you're specifically interested in and embed those specifically and see what you get for features. That would be my first thought. But that's a good question. Yep.
300 is the dimensionality of Google's vectors. I don't know.
You can
Special about 300.
You can train them, they can be converted to be less. And so often when you train your own, you tell it the dimensionality. So yeah, this is what Google's is.
Is there a particular reason for using logistic regression? Is it just good for the example, or is it typical in application?
It's a simpler model, so there's not a lot of cross-validated terms that have to be trained. That's why I like it. And the other reason is it has regularization. So when you start stacking a lot of terms together, this sort of Frankenstein model at the end, you may want a regularizer in there.
Okay, thanks.
But you could try lots of other models too. Hi.
It's 1 o'clock.
I'm sorry?
It's 1 o'clock. So
Yep, no problem. We're done. So I fit 3 models and just compared them. I was thinking around with something. Speaking strictly from accuracy, my combined model did a little better. But again, you could look at other error metrics as well. I was thinking around with that, but we're getting called. So everyone has the answers. So if you have any questions, I'm happy to discuss further outside.